everybody today? All right, so I'm going to try and finish the notes on chapter 5. We may not get the last couple of slides done. So on Monday is the review session, so if I need to, I'll finish the last couple of slides on Monday, and then we can do some review questions and things, okay? But I'll try and get done today, but I think there's just a few too many to get through, and I don't want to rush it and it be garbled for you, so we'll see how it goes. Oh, good grief. Sorry, let me do that again. All right. So we're going to look at sliding filament theory. You might have covered this before in AMP. I'm not sure, but if you did, that's good, because then this will be review. So this is best explains at the moment how the protein filaments in the muscle cell can interact and contract to generate force. It's an old theory now, 1954. So, you know, you've got to think that probably there's not much different to this, that it must be relatively accurate. Otherwise, I think we would have had another theory by now. So we're going to look at how the actin, the thin protein filament, and the myosin, the thick protein filament, slide across each other. Okay? And we want to understand this so that we can understand how force is produced and transmitted to the skeleton. And we also want to understand that the number of these complexes that are formed, so the number of myosin heads that are attached to actin filaments, drives how much force can be produced at that time. All right, and that becomes important when we start looking at angles to force production and ideas like that. So the next slide goes through this as a list. And so the slide after this does it as a picture. So it depends which way is the easiest for you to learn. Some people like it written down as a list, other people like the picture. All right, so use whichever is the most useful for you. So at rest, when the muscle is at rest, okay, the myosin head cannot attach to that receptor site that we talked about on actin, right, on the troponin. So the active site is covered over by the tropomyosin, the green and yellow kind of ribbon. That covers up the site when the muscle is at rest. Right? So the first thing we have to do is change the resting membrane potential. Right? So the electrical impulse is generated at the neuromuscular junction if enough acetylcholine attaches to the receptor sites on the sarcolemma. Then that will reinitiate the action potential. The action potential will spread across the surface of the muscle cell, so across the sarcolemma, and then goes down into the T-tubules that are the tubes that run down through and into the muscle cell. Right? The T-tubule lays quite close to the sarcoplasmic reticulum, the netting material that's wrapped around. And the sarcoplasmic reticulum contains calcium ions, which play a crucial role in muscle contraction. So when the electrical impulse runs down the T-tubule, it stimulates the sarcoplasmic reticulum to release calcium into the muscle fiber. All right? That calcium will then bind to the troponin part of the actin molecule, and as it binds, it changes the configuration of the molecule a little bit. And that allows tropomyosin to shift off the receptor site, and then the myosin head can attach, and we have a cross bridge. Right? Remember that the head of the myosin molecule is on a hinge, so it can move. Right? So once it's attached to the actin, bless you, once it's attached to the actin, then it can move, flick, and drag the actin with it. And so we see the shortening. Remember that one end of the actin is attached to the Z line, and so as the actin is dragged towards the center of the sarcomere, the Z lines move in, and we see shortening. Now, if you're like me, it's a lot easier looking at the picture, right? But as I said, some people like the written list. It doesn't matter as long as you can follow the process. Right? So here's our motor neuron. Here's our neuromuscular junction. The acetylcholine is flooding across and attaching to receptors. And if there's enough acetylcholine to meet threshold, it will depolarize the muscle cell, right? So we'll see the impulse run across the surface of the muscle, down the T-tubule. So here's the larger version. Here are the little T-tubules. The blue netting is the sarcoplasmic reticulum, right? Then we see calcium released into the cell, and the calcium attaches to the troponin, which causes a shift in shape of the molecule. Tropomyosin moves away, and we see the cross bridge formed. All right? And then when the cross bridge is formed, the head flicks, and the actin is pulled across. Questions? So there's some rather super diagrams in this chapter showing how this works. So here's the myosin, and it flicks, here it flicks, and the movement will be, the movement would be to the right. Okay. I have, though, an animation for you to watch, because I think the animation is even more useful than the pictures are. Right? I think that sometimes when you can, even looking at the pictures, it's hard to visualize how this can happen. So let me make sure I've got, oops. There we go.
You use muscles every day to do activities. This woman is using muscles to breathe, circulate blood, and move her hand to take notes. Your cardiac and smooth muscle tissues are involuntary. You do not consciously control their actions. Skeletal muscle works under voluntary control. Skeletal muscles are composed of bundles of muscle fibers. Muscle fibers are long cylindrical cells containing several nuclei. Muscles will contract or relax when they receive signals from the nervous system. A neuromuscular junction is the site of the signal exchange. This is where the synaptic bulb of an axon terminal and muscle fiber connect. Muscle fibers are composed of many myofibrils. A myofibril contains contractile units called sarcomeres. Sarcomeres run adjacent to one another down the length of the myofibril. Each sarcomere consists of alternating thick and thin protein filaments, giving skeletal muscle its striated appearance. The muscle contracts when these filaments slide past each other. The thick filaments are myosin, which are anchored at the center of the sarcomere, called the M line. The thin filaments are composed of the protein actin, which are anchored to the Z lines on the outer edges of the sarcomere. Because the actin filaments are anchored to the Z lines, the sarcomere shortens from both sides when actin filaments slide along the myosin filaments. Although the action between the filaments is described as sliding, the myosin filament actually pulls the actin along its length. The cross bridges of the myosin filaments attach to the actin filaments and exert force on them to move. This action is known as the sliding filament mechanism of muscle contraction. In this model, the sarcomeres shorten without the thick or thin filaments changing in length. A contraction begins when a bound ATP is hydrolyzed to ADP and inorganic phosphate. This causes the myosin head to extend and can attach to a binding site on actin, forming a cross bridge. An action called the power stroke is triggered, allowing myosin to pull the actin filament toward the M line, thereby shortening the sarcomere. ADP and inorganic phosphate are released during the power stroke. The myosin remains attached to actin until a new molecule of ATP binds, freeing the myosin to either go through another cycle of binding and more contraction, or remain unattached to allow the muscle to relax. Muscle contractions are controlled by the actions of calcium. The thin actin filaments are associated with regulatory proteins called troponin and tropomyosin. When a muscle is relaxed, tropomyosin blocks the cross-bridge binding sites on actin. When calcium ion levels are high enough and ATP is present, calcium ions bind to the troponin which displaces tropomyosin, exposing the myosin binding sites on actin. This allows myosin to attach to a binding site on actin, forming a cross bridge. Calcium ions are stored in the sarcoplasmic reticulum and are released in response to signals from the nervous system to contract. Neurotransmitter molecules are released from a neuron and bind to receptors, which depolarizes the membrane of the muscle fiber. The electrical impulse travels down the T tubules and opens calcium stores. Calcium ions flow to the myofibrils where they trigger a muscle contraction. As the actin and myosin slide along each other, the entire sarcomere shortens as the Z lines draw closer to the M line. As the sarcomeres in myofibrils contract, the entire muscle fiber will shorten. When muscle fibers contract in unison, a muscle can produce enough force to move the body, allowing you to take notes.
Hopefully the animation helps a little bit. I really like animations. They make it much clearer in my head what is going on. So we finally see why we need ATP for muscle contraction, right? We need that ATP to attach to the myosin molecule to stimulate the cross-bridge formation, and that's where we need ATP for. Okay? So we need to have ATP to form the cross bridge, and then we need an ATP to put the myosin head back, to detach it. All right? And that energy is used to cock the head back and attach. And that's going to continue to cycle over and over as long as calcium is available in the muscle cell, all right? And the calcium will be available as long as there's an electrical signal from the central nervous system for the muscle to contract. So until that signal stops, calcium's going to be available and we're going to see muscle contraction. When the signal stops and the action potential stops, then calcium is pumped back into the sarcoplasmic reticulum for the next signal, all right? Once the calcium moves off the troponin, then we see a change in the molecule and the tropomyosin covers the active site and the myosin head can't attach, all right? So what we have then is calcium being a key component for this contraction as well as ATP, all right? And we have to understand that the muscle can only contract, right? There's no mechanism in place for the muscle to relax, okay? So once the ATP is attached to the myosin head and the calcium has gone, then the muscle has to rely on external forces to stretch it back out to resting length again, right? There's not a mechanism to stretch it out. So that external force can be gravity, or it can be the action of the antagonistic muscle on the other side of the joint, right? So there are a couple of ways that an external force can be applied that pulls the bone and stretches the muscle back to its resting state. All right? So we can't uncontract the muscle. We can only stop the contraction and then wait for an external force to stretch the muscle back out. Does that make sense? So I want to talk a little bit about how does the central nervous system understand the force production and the length of the muscle at any time, so that it can tweak motor patterns and coordinate motor patterns so that they're precise and we can repeat skills over and over in the same way, right? So the brain and the central nervous system rely on sensory information from proprioceptors, right? And proprioception and kinesthetic awareness are terms that are used to explain or to represent how the body understands where it is in space or in relation to another object, right? So we have sensory organs, we've got touch and heat and pressure in our skin, we have joint receptors that send information, and in the muscles we have two kinds of proprioceptors, sensory organs, that we're interested in because of the information that they send to the central nervous system. So we've got one that is specifically within the muscle tissue itself, and then one that is placed at the junction between the muscle where the muscle is coalescing into the tendon. And they send so much information to the central nervous system that it plays a role in the learning effect, right? So if the brain turns on motor unit ABC and the force that's produced doesn't result in the outcome that was wanted, right? Then next time it does that motor unit recruitment, maybe it will turn on A, B, C, and D because of the information it got back from the first attempt, right? So it can increase the force production to make sure that the next time you land on your feet and not on your butt, for example, right? So we want to be able to repeat motor patterns. That's the whole point of training and practicing, is so that we can learn to repeat a motor pattern reliably and then put it into a competition, right? So the first proprioceptor, the first sensory organ that we're interested in is the muscle spindle. And the muscle spindle lies within kind of the muscle fibers. It lies parallel to the muscle fibers and is attached at either end. So when I stretch the muscle, I also stretch the spindle, right? So it has two jobs to do, right? It has to monitor stretch in the muscle or the change in length in the muscle, and it's going to then send information to the central nervous system, which will result in a contraction of that muscle when it is stretched. So it has a protective function in many ways, right? But it's not just the protective function, because it is sending information to the brain about how much stretch there is at any time. Okay? It also plays a role in the stretch reflex. Okay, so if I stretch a muscle very quickly, then it is immediately contracted. So we can use that, and it's used a lot in motor skills, right? Because that means I can produce greater force output if I add a pre-stretch into the skill action. So, for example, when we watch soccer players, particularly if we're looking, let's say we're looking at a penalty kick, right? If you watch the slow motion of the penalty kick, you'll see that the kicking leg is over extended, right? So there's a big stretch on the hip flexors and the quads at the back of the swing. And that stretch then adds extra power into the kick via the stretch reflex. Right? So it's now thought that there's a training effect incorporated here that allows for adjustment to the length of the actual spindle, and then that increases its sensitivity, right? So for very, very complex skills, the fact that it's more sensitive and the brain is getting maybe more information about, not always the brain, sometimes it's if it's a reflex, it'll be the spinal cord, but it'll get more information about the length of stretch or the change in the stretch, right? How fast. I have to stretch the muscle really, really slowly to kind of mitigate, to stop those spindles firing off and causing contraction. So when we are looking at flexibility training later in the semester, you've got to remember what muscle spindles are for, right, and how they work, because that plays a role in what are safe practices for stretching. The other sensory organ we're interested in is a Golgi tendon organ, GTO, and the GTO is placed at the junction of the muscle and the tendon there. So it can register force production from the muscle to the bone, right? And so its job is also somewhat protective in that when it registers large force production, then it sends a signal to the central nervous system and we get a return signal to the muscle to relax. So it responds to the force or the tension that's being applied from the muscle to the tendon. Right? So it's trying to prevent there being too much force applied to the tendon and the bone. Right? But again, it has some training effect, we think. Right? So what we're looking at now is there are training techniques to try to decrease the signal from the Golgi tendon organ. Can we decrease that signal so we don't get so much inhibition and relaxation in the muscle? Right? So think about it this way. Imagine you're trying to do a 1 RM bench press, right? So, you know, if it's your 1 RM, that's going to create a lot of force. That's the most amount of force you're capable of producing at that point in time, right? That's your measure of strength. So you're going to apply this huge force to push the barbell back up, right? So imagine what would happen if you do that and the Golgi tendon organs in the front of your shoulder and in your chest send piles of signals and your central nervous system turns those muscles off, right? Then you get bar face, right? So training allows for the feedback loop to kind of get damped down a little bit. And then we can see greater force production in the muscle. The information coming from these sensory organs is affected by fatigue. So when we're tired, when the system is tired, not when we're tired in here, right? When we are physiologically tired and fatigued, the sensory information and the return motor information slows down a little bit, and that can lead to injury, right? So when we're training, we're not just training the muscle tissue, we're training these proprioceptive pathways as well so that they're more resistant to fatigue, and then we can produce optimal performance more often, right? And this picture kind of ties the two together. It doesn't have the nerve supply from the GTO, but here's the spindle. So the spindle gets stretched. It sends a signal to the spinal cord, and synapses, and comes back to the muscle to contract. So this is a good one, like if I turn my ankle over, right, the muscle gets stretched very quickly, and we get a very quick response from the central nervous system to contract the muscle and pull the ankle back in line. Right? Otherwise, there'd be a lot more broken ankles and sprained ankles than there actually are. Okay? When I contract the muscle and really hard, then the GTO sends a signal to the spinal column, and that synapses with the motor nerve, and the signal comes back to the muscle to relax so that it doesn't get damaged, and the tendon doesn't get damaged, and the bone doesn't get broken from the force production. Does that make sense to anybody?
Yes, that makes sense.
Thank you. All right, so what kind of actions do we see occurring in the muscle tissue? All right, so we want to look at the length of the muscle at any time. Right? So it's attached at either end to bone, right? When it's at rest, then there's no calcium flooding around in the cell, there's no actin-myosin complexes or cross bridges being formed, and so it's just stationary, right? It's at rest. So I'm going to jump that next picture and go to the third one first of all, because this is the one we were talking about just now with regards to the sliding filament theory. All right? So here, in this one, there's a signal coming down the motor nerve and an action potential within the muscle, and calcium is flooding out, and we're seeing contraction. All right? Okay. And as the actin and the myosin slide across each other, we shorten the sarcomere, we shorten the muscle. Okay? So here's the other bone, and it's moving this way, we're shortening the muscle. This is called concentric action. Right? And in this situation, the force of the muscle is greater than whatever the force of resistance is, so that the muscle can shorten. Okay? So if we think about doing a dumbbell curl, right? Then my bicep, if you watch your bicep when you do a dumbbell curl, right? If I lift the dumbbell up, then you can see significant shortening in the bicep, right? But that happens when my bicep is strong enough, when it can produce more force than the weight of my lower arm and whatever the dumbbell weighs, right? And force of gravity. Okay, so we see shortening. Then we'll go back and wow. we'll go back to picture number 2, right? In picture number 2, we have force production, but the filaments are kind of, the heads are pulling, but there's nothing happening, right? So there's force being produced within the muscle, but we don't see the actin sliding across the myosin. So you can see here, there's no change in length here, right? This is an isometric action. And in this situation, the force of the muscle equals the force of the resistance, right? So isometric actions are often used in rehab because if there has been surgery in here, either at the tendon or at the bone or in the muscle itself, then I don't want movement, right? Because I don't want to disturb the healing of the injury and the surgery, right? But I do want to keep having force production to keep the strength of the muscle up. Okay. Our last picture is an interesting affair, right? This, I think, is the most interesting thing. So here, we have force being produced, but actually, the muscle is being stretched out, right? So in this instance, there's force being produced, but actually the actin and the myosin are being dragged in the wrong direction, right? So in this situation, the force of the muscle may not be strong enough to overcome the resistance. Okay? And this is called eccentric action. And in eccentric action, we see lengthening of the muscle. Doesn't mean the muscle is not contracting, right? There's force being produced, you can measure it, but it isn't shortening, it's lengthening. So this can occur in a couple of situations, right? It could be that the max force possible that that muscle can produce at that time is not large enough to overcome whatever it is it's trying to move, whatever the resistance against it is, right? So that's one instance where we might see eccentric action. Another instance that we see a lot in movement skills is when the force of the muscle is deliberately turned down to allow for lengthening in a controlled manner. Right? Okay, so when I do a squat, what are my quads doing? When I go down, what is the action in the quadriceps as I squat down? Come on, guys, I know it's Friday. You're making this very hard work. Just try. You've got 3 options. What's the action in the quadriceps as I'm squatting down? Right, so this force velocity curve is showing something that we don't always recognize when we're doing our strength training, is that the y-axis is force and the x-axis is velocity. So going to the right is getting shorter, so concentric type action. And going to the left is lengthening velocity, so eccentric action. Right? So at the point where the curve crosses the y-axis, y is 0. Right? So there's no velocity at 0. Okay? So the black dot here, as the curve crosses the y-axis, represents isometric action. Okay? So what's interesting here is that to the right is the force production from concentric action. So concentric action is always less force than you can produce isometrically in that muscle. The curve to the left represents eccentric action, and eccentric action always produces more force than isometric or concentric action. Right? So we tend to think that it's the push that makes us stronger when we're lifting, right? But actually, it's the down phase that makes us the most strong when we're training, right? And it's the down phase that makes us the most sore, which is why negatives are so hard, right? And you have to have a really good spotter if you're going to do negatives in the gym, because the whole point of negatives is to work this eccentric action, right? You work the eccentric action, but then, because you've put all that weight on the bar to work the eccentric action, you're stuffed to get the bar back up. Right? So you have to have a really good spotter to help you get the bar back up via the concentric action. So negatives are really, really effective at making you stronger. They are not a training program you should do with beginners. Right? You don't want to be doing negatives with anyone who is not experienced at weight training. You've got to have really, at least one, preferably two, really good spotters who know when to take the bar, right? And get the timing right on the spot. And you've got to understand that you are going to be really, really sore the next day or the day after, right? Because of all this force production. And that soreness is called delayed onset muscle soreness, or DOMS. Okay. Somewhere between 12 to 48 hours, right? So sometimes you do a heavy session and you get up the next day and you're like, oh, I got away with it, I don't feel too sore at all. And then you get up the next day and you're like, oh my goodness, I can't move my arms, right? Because when you generate that much force within the muscle tissue, we do damage to the muscle tissue, right? So DOMS is primarily caused by the eccentric action because that's creating the most amount of force in any movement, right? And whenever we do exercise, we damage muscle fibers, right? We do little micro tears depending upon the intensity of the work. We do little micro tears all the time. That's why we need to get lots of sleep so that we can mend the damage and make the muscle stronger. Okay? And so the soreness is because there's structural damage. You can literally see tears in the membranes and the little connective tissues. And so irritants form, we're releasing chemicals into the environment, and so we get soreness and swelling that pushes on the nerve and causes pain. Right? The eccentric action, go back to the graph. Right? The eccentric action is creating the most amount of force. So it's the eccentric muscle activity that is primarily due, to blame for DOMS. Right? So running downhill is going to make you much more sore than running up the hill. Okay? So when you're doing hills or stairs, right, going up makes your cardiovascular system work really, really hard. And so the up phase is really good for your fitness level, and the down phase is really, really good for strengthening. Someone who's untrained is going to get a lot more sore than someone who trains on a regular basis. So you've got to be really careful with your beginners and your sedentary or low active people, because, you know, I don't know about you, but when I lift, I like a little bit of soreness the next day because it tells me I worked hard, right? But a lot of people don't like that feeling, right? They don't like to be sore. So we've got to be careful how we introduce our beginners or our sedentary people, because if we make them sore, they're not going to want to come back and do it again, right? So we have to be very careful how we set the program up early on, right? We can use lower intensities, right? Much less weight. We can emphasize the concentric part of the move and help them out with the eccentric part of the move. We can use progressive overload principles, right? So we start them off very light, and then we give them a little bit more over time. We progress the intensity of the work so that we can minimize how much damage we're doing and how much soreness they're going to feel. All right? This soreness is not lactic acid. This soreness is because of the damage that's done to the muscle fibers, because of the accumulation of irritants and swelling and inflammation reactions and responses. Right? Okay, I'm going to stop there, and we'll have to do the last couple of slides on Monday before we start review. Any questions?
I do have a question, Ms. Wu.
Sure.
I know that you don't have office hours today, is it correct?
Yeah, no, not on Friday.
Okay, so only on Monday, right? Next one?
Yeah. What do you need?
Okay. It's a little bit more than just one question.
Oh, okay.
So we can talk on Monday then.
Okay. Alrighty.
All right.
That sounds good. During office hours, or do you need another time?
We can use office hours.
Okay. All right. That works.